Okay, so the approach we're going to take in this class will be a hybrid between the classical synthetic approach, Hilbert, and the analytic approach, say Birkhoff's approach. The approach we're going to follow is going to follow closely the approach taken by Moyes in his textbook, um, Elementary Geometry from an Advanced Standpoint, and then also Kay based his treatment on Moyes's, and we're going to be following kind of his work as well in his book called College Geometry, A Unified Development. Okay, and so the postulates that we're going to use will be a metric very similar to that of Birkhoff, and it will be used to define between, and we'll use this metric to help us prove Hilbert's axioms of order and continuity as propositions. So they won't be postulates or axioms, they'll actually be propositions of the way we're going to do the geometry. This is going to definitely move our development along much faster. It's going to get at this important concept earlier. And however, we're still going to try to follow a mostly synthetic approach for most of the rest of our stuff. Now, after we prove Hilbert's axioms of order and continuity, you can, of course, use them. And, of course, you can actually prove the rest of the, or many of the rest of the betweenness properties using those axioms. Well, they'll be propositions, part of a proposition, the way we're going to do it. But you can also sometimes get an easier proof if you'll go back to some of the results that we get from having a distance metric. Okay, so there's a tab here for unified geometry statements that will be true in unified geometry. We'll kind of briefly talk about those in a minute, and then more detail later. Okay, so we're going to take the following definition of a distance metric. Okay, so a distance metric is a function d mapping the set of ordered pairs of points in a geometry into the set of real numbers, such that for any two, not necessarily distinct points A and B in the geometry, the distance between a point and itself is 0. Distance of A, comma A is 0. And I have, by the way, slightly abused the notation here, as we typically do when we do functions of two variables. We're doing a function of an ordered pair, and I guess technically this should probably look something like this, where we have we take an ordered pair as an input and then find its distance. However, we're going to drop that extra parentheses here. Okay, so basically should have one set of parentheses for the function notation and another set because the parentheses of the ordered pair is the input. We typically drop those as you did like in Cal 3, for example. So the distance from A to A is 0. The distance from A to B is positive if A is not equal to B. And we put these 1 and 2 together. This is called positive definite, that the function is always a non-negative real number for the output. So I could have just said, to begin with, the function maps the set into the set of non-negative real numbers to begin with, and then I could have avoided stating number 2 and just, well, I still need to show that the distance is positive if the points are not the same. Okay, so then we finally have the third characteristic is the distance from B to A is the same as the distance from A to B. That's kind of a symmetric property. So it takes just as long to get just as far from one point to the next as it is back. The output of this function is called the distance between the 2 points, and we'll use the notation AB for the distance from A to B. We say that the distance metric is unbounded if the range of D has no upper bound. For example, in other words, what that means is D is onto the set 0 to infinity. Okay, and we say the distance metric D is bounded if and only if the range of D has an upper bound. And specifically in spherical geometry, the way we're going to do it, that upper bound will be pi. So d is onto the set 0 to pi, that interval. If the geometry has a bounded metric with an upper bound of some number u, in our case pi, then any 2 points A and A prime with the distance from A to prime equal to u are said to be antipodal points. So think of this as the North Pole and the South Pole on at the Earth, for example, if we're doing spherical geometry. Now you do not have antipodal points in a unbounded geometry, okay, or an unbounded metric. So let's note that points do not exist if the metric is unbounded, as it is in Euclidean, taxicab, and hyperbolic geometries. So the antipodal points thing is really, for our purposes, is really just going to come into play in the case where we're dealing with spherical geometry. Okay? So what are we saying? We're saying we can come up with a number that we call the distance between the 2 points. That's basically what we're saying, and it's a positive number or 0. So another property we're going to prove later on is called the triangle inequality. We'll prove this as a theorem later, proposition. And it says for any 3 not necessarily distinct points, A, B, and C, the distance from A to B plus the distance from B to C is greater than or equal to the distance from A to C. A set of points with a distance metric satisfying the triangle inequality is called a metric space. And so metric spaces form an area of mathematics that is an area of study. And so they sort of generalize this idea of Euclidean geometry where we measure things a certain way. It sort of generalizes this. And so it's kind of what we're doing is we're looking at these 4 geometries that we're looking at have different metrics. Okay. In the case of hyperbolic, Euclidean, and taxicab geometries, we can always think of those as, well, Euclidean and taxicab geometries, we can think of all those as points in the Euclidean plane with a different metric. We can think of hyperbolic as being points, some of the points in the Euclidean plane, but with a different metric. Spherical geometry, can't really put it in Euclidean plane, but we can put it on a Euclidean sphere. Now, one of the things that's generated by metric spaces is a concept of an open set. For example, if real numbers on a number line, we can talk about open intervals, which are open sets. So if we generalize the concept of metric spaces to focus on the properties that open sets have, then we generate something called a topology. And topology is a major area of study in mathematics, and it's very closely related to geometry in some ways. So that's about all I'm going to say about topology for quite a while, but just realize that metric spaces, topologies are some important mathematical concepts. Now we're going to define a coordinate system for a line to be a one-to-one correspondence F between a line L and the range of the distance metric, such that for any points P and Q on line L, the F of P minus F of Q, absolute value of all that, equals the distance from P to Q. The output of this function is known as the coordinate of the input. A point with coordinate 0 is said to be the origin of the coordinate system. So what we're doing is we're taking points on a line and we're assigning them numbers in a one-to-one way. Okay? And it's one-to-one and onto the range of this distance metric. So in the case of the Euclidean let me take that back. We want to change that a little bit. For in the case of the real numbers, we want it on the entire real line. between a line and the set. Okay, minus and the let me call this set R. Now let me call it a set C for coordinates, where C equals the set of real numbers when the distance metric is unbounded, and C equals the interval. Let's see, we want to do minus U to U when the distance metric is unbounded, where U is the upper bound, the distance metric. Okay, I think that's going to fix it. Okay, so what we want, let's back up and see if we can say this the right way here. So a coordinate system for a line, it's a one-to-one correspondence between points on the line, and let's just say if it's an unbounded metric, between points on the line and the real numbers. So we're assigning every point on the line a real number, and every real number gets used. So there's a one correspondence between the lines, points on the line, and the real numbers. So every number is a real number line, okay, if it's unbounded. On the other hand, if it's bounded and the distance metrics only goes up to U, then we want to be able to define it in such a way that the range of this coordinate system just goes from minus U to U, including U but not minus U. Okay? And we want to do it in such a way that if you take the coordinates of the two and subtract them, then you get the distance between them. The output of this function is known as the coordinate of the input. A point with coordinate 0 is said to be the origin of the coordinate system. This definitely works for the infinite situation. Let me do a little bit of thinking about this. I may get back to you on the. You have to be a little careful with spherical geometry because of the way you do the coordinates. So I may get back to you on modifying that slightly for spherical. So the ruler postulate says there exists a distance metric for this geometry, and every line has a coordinate system. Okay, this is essentially what Birkhoff is saying in his first postulate. Okay, so the ruler postulate says that any line can be thought of as a number line, and here is what right here is what a Euclidean number line looks like. So notice that these are here's a bunch of points given here, and some of their coordinates, some of the points there are listed with their coordinates. Of course, there are many other points that are there that you can see, but they're not. Their coordinates are not listed here. Just line up a little better. Okay, now with this we can define what we mean by between. We say a point B is between points A and C if and only if first of all, A, B, and C must be collinear, and secondly, AB, the distance A to B plus the distance from B to C has to be the distance from A to C, and we denote it as A-B-C. Furthermore, we will use the notation A-B-C-D to indicate that A-B-C and B-C-D. So in other words, A-B-C-D indicates that B is between A and C is between B and D. So we'll take that as a definition. And here's a Euclidean illustration of B being between A and C. Actually, you can make B equal to A or C the way this is done here, but otherwise you have B between. Notice that C is not between A and B, A is not between B and C. If you add these two distances from A to B and B to C together, you get the length of the whole thing from A to C. But if you added, for example, A to C plus B to C, you definitely do not get A to B. It's much longer. A line segment is a union of 2 points, okay, called its endpoints, and the points between these points called the interior points. So that's going to define endpoint, and it's going to define interior point for a line segment. And we use the notation AC with the bar on it to be equal to that, AC union the points B that are between A and C. And the length of the line segment ABC is the distance between its endpoints, which we call AB. And so you see a Euclidean line segment illustrated up there. A ray, sometimes called a half line also, is the DE is the line segment DE along with all points F that are out here. Okay, well, I made the F where it could be moved in here. Not F in here, but F out here where E is between D and F. So you see a Euclidean ray illustrated there. Okay, so that defines some basic things. We'll come back in our next video and talk a little bit about what some of the things we can do with these basic concepts in our unified geometry.